Okay, so now, as I mentioned, you can use the differential as a tool to calculate the change of and functions by a little bit. So this is a simple graph I mentioned to you. So imagine you have a function y, then for example, imagine initially you have a values of a function f x at a, then the values of the function is at a. Then you make the x to change by a little bit amount, which is delta x. So dx here refers to the change in the variable of x, and that amount is delta x. So delta x, normally when you say delta x, this refers to some discrete number, say for example 0.1 or 0.2. Okay, so delta x normally refers to a finite change in the number. So when x change by delta x, then fx will change to this number. Right? This is a number which has a coordinate of f at a plus delta x. Right? So the difference between this line and this line is just this. Right? So we call this delta y to represent the change in the functions. So this is usually what we want to know. If you have a change of x by 0.1, then what is the corresponding change in delta y, right? So according to the definitions, the delta y, which is the exact change in the function, could be approximated by this delta L, where delta L is the derivative of the function multiplied, well, delta L here is then just the differential of the functions at the point x equals to a, right? df is just the derivative of the function at the point a multiplied with the change of the variable x. So here, as I mentioned earlier on, you can calculate the derivative of the functions at a, then you can make this just to be the change in the function. So delta y is the exact change in the function when x changed by delta x. So to obtain delta x, you just have to calculate the differential of the function and at a. Now, before I proceed on, you sometimes want to ask, why don't you just calculate the delta y exactly? Right? Why don't you just calculate delta y exactly? That is actually sometimes not that difficult. But you think about it, you can actually calculate the exact value by an approximation, and you pay only a little bit of price. The price is a slightly change in the accuracy of your calculation. So if you require an accuracy of say only 1 decimal point, then it's worth to just calculate the change in y by using approximation, because approximation may be accurate up to 1 decimal point. But if you want an accuracy which is like 0.0001 accuracy that with many decimal points, then only you would think of calculating the difference in y by using exact method. So there are two methods to calculate the change in y when x changes by a little bit. Either by exact calculations, that is, you calculate what is the values of f at a plus delta x, you calculate what is the values of a, then you take the difference. That will give you the exact change. But if you use the approximation, you can still get a good idea or good guess or good estimations of this delta y by simply calculating the derivative. Right? The derivative is of a function is easily calculated. If you know the functions, you know what fx is, then calculating the derivative of ff is quite easy. Then you multiply the derivative by the change of delta x. That itself would give you a good idea of what delta y is. So delta y is roughly equals to this. So this is your differential. Differential is a good approximation to the exact change in the values of y. Okay, so calculating derivative is usually easy, right? It's usually easy. So so you can use this approximation in the next example, which I'm going to show you now. So if you have, say, a functions of a circle, right? Function of circle in terms of its area. So the area has a function a, which is given by let me draw on this. So you have a functions of a which represent the area of a circle, which is equal to pi r squared, right? So then the question asks you, if the r change from 10 meter, so originally the area, the r is equals to a equals to 10 meter. Then you change the r by a little bit, say 0.1 meter. 0.1 meter, then you ask what would be the change in delta A. You understand the questions? Originally, the circle has an area of pi r squared, where r is equals to the area, is equals to A equals to 10 meter. Okay, so then when the area change, when the radius change by 0.1 meter, then will cause A to change by a little bit. So the question is, what is the change in A? So you can easily represent these situations on the functions, but I think there's something wrong with my with the screen. So let me go to my laptop that give you a better pictures, okay, which is not distorted. Okay. So this is the graph that I want to show you. So you plot the function of A, and you plot the function of area as a function of A, of R. So originally the values of the radius A is here. So you look at this point. So this is the values of the function A. So when you change R by dr, so this is a width of dr, then when R change from A to A plus dr, then the values of A will change from here to here. This is a curve of the area as a function of R. So at this point, the area is A divided at A plus dr, and you know what is the function of A. So the exact change is delta A, right? So it's just the values of A at A plus dr minus the values of A, okay? So, but then you look at this line. Right? This is actually an approximation. It's an approximation, it's a linear approximation to the function at the point R equals to A. So Lx here represents a linearization of the functions at the point here. So if you were to calculate delta A, you can actually calculate this delta A using the differential of the functions L at the point R equals to A. So the differential here is actually the linearization that we mentioned in the first part of this lecture. So A prime A refers to the derivative at the point A, but then you multiply this differential at point A with dr, it actually gives you a differential, which we call delta L. Right? This delta L is then a good approximation to the delta A. Okay, so so we are almost done with this, but it's already 10:57. So I have 3 more minutes to proceed with my lecture. So this is an example of the solutions. So you calculate the delta A using exact value. Then you can also calculate the differential as an approximation to the difference in A when A changed by 0.1. Then this is just the answer. So the exact values is this. So this is a change, this is the values of A when R changed from 10 to 10 by plus 1. Then the difference between this number and this number give you the exact change in the area. But this term gives you an approximations in terms of the linearization of the functions or the differential. Right, so here the differential is just a linearization, or which is closely related. So this is the answer, which is obtained to be 2 pi and approximation. Then the exact values of the delta A is actually 102.01 minus 100. So if you take the exact change, then you find that the exact change is more or less given by the approximation. Okay, so that is an illustration of the applications of the differential to calculate the change in the area. Right. So here, this is the differential. So happen that this differential is very like is just the linearization of the function at the point A. So we have illustrated the applications of linearizations as well as the differential as a way to approximate a function which is not curved. When x changed by a little bit, then the change is just given by the linearizations or the differential. Okay, so that is all for today's morning lecture. I'll stop recording here now.